a few remarks. Okay, the first remark is that, as you see, I proudly put my second affiliation here. And when I joined the staff of the Center of Formal Ontology, I was curious, what does it mean, formal ontology? As curious as everybody else is always when I cite this name. And the official explanation is that we use formal, say mathematical methods to investigate some problems, philosophical problems, or better, ontological problems. So I tried to keep to this, to follow this path, and this will be the spirit. But this is by chance, because what I want to tell you is exactly how it was created on the fringe of the other activity, purely in mathematical physics of mine, and then this fundamental problems reappeared somehow here. The second remark is that the problem itself, so identical particles, I think is very popular. So there are hundreds of papers treating this problem from purely physical or mathematical point of view, but also a lot of, I would say, more fundamental, concerning more fundamental treatment. Because, you know, it happens, fortunately, that philosophers and physicists often attack the same problems. I always suspect that there are completely different aspects which are interesting for both of these groups. So at least they see some differences with respect to what is really deep and interesting. So the best thing is to present a lecture in which everybody will find something which is deep and interesting, but it is very, very hard. So please forgive me if what I want to say and what I will say will be trivial for everybody. So for physicists as for philosophers, because it's in principle it will be very simple. As I told you, there are a lot of papers concerning the problem of identical particles, and I also contributed to this plethora of papers when I worked on the proper definition of what does it mean that identical particles are somehow quantum correlated, that there are something which is really important in correlation among them. So that's why this entanglement appeared here. And as I told you, on the fringe of this, these fundamental problems reappear. So let's start. What is really identity? Okay. So despite that we often say that two objects are identical in our world, there are in fact no identical, so different but identical object. And this is actually Leibniz Principle, which is, okay, more or less formally written here, rather informally, because I quantify over all properties without saying what are properties. But please let me take this burden from my shoulders to define it more precisely. I think that intuitively everybody knows what does it mean. If they are two objects which have all properties the same, so in fact they must be identical, must be the same object. Okay, so in a sense there is a tension between defining that something is identical and differentiating between two objects. Okay, so we cannot do this, because if we already differentiate, we say that there's one and there is a second one and they are identical. We'll already differentiate between them, so they can be identical because we know which one is. One is the first one, the second is. And this is actually exactly the principle, the Leibniz principle, okay? So this is also a converse of, which is also from time to time treated as a part of this principle, which is definitely very easy to understand and without no controversies. If the two objects are identical, so they have the same, all the properties are the same. Okay. So so what are the, I would say, morals out of that? So classical particles in physics are always distinguishable, okay? Which is exactly the same as to say that no two particles can be in the same state. Okay? And the important thing for what will follow is that we can label these particles. You can say this is the first particle, this is the second one, just put the labels on them, okay? And they will somehow keep these labels during their lifetime, okay? So in a sense, they always fulfill this Leibniz principle. By the way, sorry for the misprint in the title in the program, which is my fault, not the fault of organizers in Leibniz names. Okay, so both of this, I would say, this original Leibniz rule, which is this identity of indiscernibles, and the converse of that are fulfilled. And as probably everybody knows, a situation in quantum physics is a bit different. Why? First, obviously, our description of states in quantum mechanics is very different from what we do in classical mechanics, because we use states in vectors in Hilbert space, or maybe operators in Hilbert space, to describe states of physical objects. But let's start from the, and for if we have only one particle, this is everything is okay, so everything is clear. We have a Hilbert space, and then states are vectors or operators. It depends whether we decide also to in our description so-called states acting on this space. Okay, so from the principle of linearity of quantum mechanics, so it means that if something is a state, so the linear structure, which is already visible on the level of a single particle. Okay, so if something is a state and the other, we have other states, so the linear combination of this is also a legitimate state of a system. So if we extend it to the systems of many particles, so we are confronted with the fact that we have to describe this in a tensor product of Hilbert spaces. Okay, so if the particles are really distinguishable, okay, we have one electron, one proton, so for some reasons we can differentiate very well between the two. So this Hilbert space of the whole system, of this combined system combined out of many subsystems, is a tensor product of the individual Hilbert spaces, and to some extent, we can say, okay, each of these particles lives or belongs or is connected with one of this Hilbert spaces which together form a product. And so they can be labeled, okay, and this label somehow are inherited by the object or these particles which are connected with this particular space. So everything is okay. Obviously, this leaves a lot of room for other quantum phenomena which are not present in the classical world. But what concerns the distinguishability or identity or something like that, nothing has changed. Okay, so these labels are the labels of Hilbert spaces and at the same time labels of the particles. So everything. So this is something which is exactly the same. Looks exactly the same in classical world. So there is no problem. But as everybody knows, there are in quantum mechanics we have these particles of the same kind. Okay, so usually we call them identical particles. And they're either bosons or fermions, okay? At least in three-dimensional space. We can have other statistics if we consider for a two-dimensional space. But let's stick to this fundamental distinction between bosons and fermions. So the particles of the same kind, or as physicists call them, identical particles. So mathematical, I would say, equivalent of the statement, so maybe even a part of definition of bosons and fermions, is that the wave functions or the states, the wave functions are completely, states are completely symmetric and anti-symmetric. Everything still lives in this tensor product, but the states are symmetric and anti-symmetric. So usually the logic in physics of introducing this will be different. So you first say that what does it mean that they are identical, and from this you derive the fact that the states should be symmetric or anti-symmetric, but this is not a problem here. So let's say that we know from other sources that they're symmetric and anti-symmetric. So why then we can say that the particles are then indistinguishable? Okay, so this is an example. So in a sense, if we now all insist that each Hilbert space corresponds to some particle, okay, so the states of this, what lives in this particular Hilbert space, so in all the states are the same. So there is an example which somehow illustrates this very easily. What does it mean? So if we have a completely anti-symmetric two-particle states in product of two Hilbert spaces, okay, identical Hilbert spaces, okay, so these are this label connected. So we think that these are connected with some particles, okay, so this is completely anti-symmetric state. And then if we restrict this, okay, so we insist that we make, for example, measurements only in one of the laboratory in which this particular particle should live. So we have to calculate the states in these subspaces by the obvious procedure from quantum mechanics and by tracing out other degrees of freedom connected with the other part. And in both of these subspaces, the state is the same. Okay, so that the particles are really in the same state, and we can not differentiate between them by any kind of physical experiments. So it's better than to say that they are in the same state rho rather than to say what one is commonly also used, that one is this state psi, the second in state phi, but we don't know which one. Okay. So these are the results of this reasoning. So all n particles of the same kind cannot be distinguished upon their physical properties. So measurements in each subspace will give the same results with the same probabilities. The labels now do not refer to individual particles and consequently cannot individuate these particles, so differentiate between them. So apparent conclusion that quantum particles of the same kind violate Leibniz principle. Okay? Because they all have all these properties the same, and definitely there are n of them. Okay? This seems to be in the accordance with what is usually met in handbooks of quantum physics. These are citations from two, say, modern handbooks of quantum mechanics. The one is from Perez from 2003. A quantum system may include several subsystems of identical nature which are physically indistinguishable. And any test performed on the quantum system treats all the subsystems in the same way, and it is indifferent to a permutation of the labels that we attribute to the identical subsystem for computational purposes. I put it in red because definitely I feel that this, what is red, needs some interpretation, and I will tell you why. This is from Tanucci's handbook, and this is the citation. The two particles are said to be identical if their intrinsic, whatever it means, properties, mass, spin, charge, etc., are exactly the same. And once again, no experiment can distinguish one from the other. So what are the consequences of such definition? So definitely identity of all one particle states, which are caused by symmetrization, applies to all particles of the same kind. So in principle, we should not distinguish between an electron in our laboratory and another one on the moon. So anti-symmetrization should take into account both. Okay? So we should always, when we speak about the properties of a hydrogen atom in our laboratory, we have to take into account that there are some electrons also in other parts of the universe. And so no interaction or other circumstances can change this. This applies also to situation when, for example, going to the classical limit is justified. Okay, so we want to somehow describe some system for some reasons in the classical way, okay, or semi-classical way. So even in the classical limit, the synthesis should not differentiate between electrons. So even in the classical case, the Leibniz rules should be invalid or should be violated. Okay. On the other hand, and this is to comment a little bit about this, what I put in red in the previous transparencies. In the same textbooks, you can find the following formulations. So note that it is meaningful to ask questions about the electron closest to the nucleus or about the most distant one, but not about the electron labeled 1 and 2. So in a sense, you can differentiate between them because you can say one of the electron is closer to the nucleus, the second one is farther. And on another place, no quantum prediction referring to an atom located in our laboratory is affected by the mere presence of similar atoms in a remote part of the universe. So how to understand this seemingly contradictory statement? Okay, so should we actually take into account the fact of the existence of all electrons in the universe when we're talking about when we are investigating the properties of the electron in our laboratory or not. Okay, so as usual, so first thing is that we have to say what we understand by particles in quantum mechanics. Okay, so the concept of a particle is purely classical. Okay? So particles are objects which are well localized in space. Okay, so in quantum mechanics we have a variety of states, but some of them are better from the point of view of talking about particles. So, for example, what would be a good candidate, and is actually a good candidate, and this is how it is usually understood, the particle is a well-defined, well-concentrated or well-defined, a well-localized single particle state, so wave packet with a small spread in space, because they follow classical trajectories, as we learned yesterday from the lecture about Ehrenfest theorem. Okay, but the notion of being well localized is dependent on the actual measurement setting, and this is the main message and the main achievement of this. What I think is I will report is that I can quantify this somehow. Okay, so look, if you have such a situation like here, so usually when you finally it comes to the problem of measurement, you have to define how you perform your experiment. Okay, so if the wave packets are well localized, far from each other, they definitely define two distinguishable objects. Okay, so what does it mean? So that if I perform measurements, so there is no possibility that the presence of the one object here can trigger, in a sense, a response from the detector elsewhere. Okay, so that's why we do not need to bother about the presence of electrons on the moon, and this is obvious, because our detectors never are. So the response of our detectors is never triggered by them. Okay, when we investigate something in our laboratory, and then the anti-symmetrization does not. It can be shown that anti-symmetrization of this function does not influence in any way predictions which we do here. On the other hand, if these two wave packets are even well localized, but there is a non-negligible probability of triggering, say, this right-hand detector by the presence of particle, this wave localized wave packet to the left of him and vice versa, then this fact that these are identical particles plays a role. So how to quantify this? So first, we can quantify these probabilities. Okay, so of triggering the detectors which are not supposed to measure what we want to measure. Okay, so let's say that these states, this A and B corresponding to this wave packets, and then we can calculate the probability or amplitude of probability. Okay, so to detect this is actually a product to detect this on the other side by the other detector. Okay, not this one which are intended to measure the properties of our electron. Okay, so there are two such possibilities, okay, and then if they both are 0, so it means that initial preparation, initially we prepared already distinguishable particles, and so in a sense this measurement reveals the source of this whether it was on the moon or on Earth, okay, so one detected on the moon, one on the Earth. On the other hand, if they do not vanish, this means that they definitely can influence our measurements on the left hand side by the fact that this is a very extended laboratory, okay, and then the presence of the electron there influences our measurements here, okay. But this is not the whole story, because if it happens that after the measurement these states are orthogonal, we can differentiate between these two states by performing once again the same kind of experiment. Okay, so you can always differentiate between orthogonal states in the Hilbert space. So if you assume, as usually, that these measurements are represented by some projection operators, you simply and you assume that this after measurements they are orthogonal, so it means this equality. So the states, so the particles become effectively distinguishable, so can be discriminated by another experiment of this kind using similar detectors. So that's why it is worthwhile to introduce some quantitative characterization of this, namely something which we called effective indistinguishability, and this is simply the product of these two quantities. Okay, so this projections on the other side. Okay, and this definitely takes into account the detector settings. So now you can say that the full experiment actually consists of measuring, of using this detectors to detect the presence of the particles, and okay, and then you measure some other physical quantities. I don't know, angular momentum, spin, or whatever of this, which are somehow encoded in these additional operators here. So these are observables of, I would put here quotation mark, internal degrees of freedom. So you can perform this kind of experiment, okay, decided by this projection operator, and then you can reconstruct the state after the measurement by such a tomographic procedure. So you simply use the complete set of these internal observables to reconstruct the state. Okay? And now, what about distinguishability? So the proposed formalism of quantifying this distinguishability can be used to analyze various scenarios using these three parameters which I introduced. So this left-right probability of triggering the particular detector, and this something which we called effective indistinguishability. So for example, depending on the value of gamma, we can observe measurement-induced distinguishability of initially indistinguishable particles. And this is the most important thing, so that the distinguishability reappears in quantum mechanics if you perform particular kind of experiments. Okay, so you can then differentiate between the states which are particles which are initially in the same state in the sense I explained at the very. You can also control, or I would say report, evolution of distinguishability of initially distinguishable particles. For example, one of the moons, the second on the Earth, and also if you I would say construct a special measurement environment, you can observe what happens to this particular case, and in some cases you can lose this perfect distinguishability. And what is to connect it to the title of my talk, of my talk, is that you can also control or observe or report using these 3 parameters the fact that some other purely quantum mechanical properties, like for example this quantum correlations, which we usually call entanglement, disappear on the classical level. Okay, so with this distinguishability also could be connected, need not, but could be also connected, loss of this correlations, the purely quantum correlations, which is also some contribution to why we do not see quantum correlation on the classical level. And the overall, I would say, statement, so important statement is that for vanishing this effective indistinguishability, so particles can be always treated as distinguishable. So the symmetrization and anti-symmetrization does really not influence non-classical correlations. So the most important conclusion that distinguishability is very strongly determined and actually is by the measurement process, and this is actually the measurement process is, as probably everybody could expect, triggers the fact that, or is in the source, is the source of the fact that classical particles are actually distinguishable and quantum mechanical particles could be not. Okay, so this is the paper in which we elaborated all this problem. Thank you very much.
Fresh. A naive question. Detectors, I understand, are classical objects. If you have non-quantum detectors, does it change anything?
Not necessarily. It's usually as you already mentioned, it's very hard to define what does it mean classical, what does it mean quantum. Okay, but usually there is some quantum process involved this, but at the very end, you have to look at the gauge and say, okay, the value of this, because the pointer pointed to 1/2. Yes, we are classical. So at some stage, it must be translated into this, that, you know, this pointer pointed to 1/2, so it means that the value is 1/2, yes.
Okay. What about points in space-time? I mean, if gravity is present, general relativity gives us such statement that points are indistinguishable, experimentally, I would say. So does it mean they are quantum?
So, okay, so certainly I cannot say anything very clever about that, because this is the main problem which we have now, okay? So what is actually the influence of gravity, or how gravity influences quantum mechanical phenomena, okay? So this is a very general statement, okay? One aspect of this is to construct a fully quantum theory of gravity or something like that. But you can always say that even if it is classical, it has some influence, okay? So, for example, for the decoherence process and something like that. And then it is, I don't know, okay? So I believe that this has something to do, and the gravity definitely plays a role in making quantum mechanical world classical world, okay? So, but how it is done, I don't know. And probably nobody knows until now, okay? So this is a strong belief. But this is definitely plays a role in the transition from quantum mechanics to classical. So from quantum picture to classical picture. Okay.
Maybe just a comment that that it's a very elementary observation. What people did recently, that gravity leads to may lead to quantum entanglement and superposition, because quantum mechanics is not actually interested in the source of interaction. It just, it just reacts when the interaction is there. So in that sense, we already have some, some connection,
yes.
right?
Yes.
Okay,
so this is one of the sources of my belief that it is very important also. Yes.
And while the